Let's do one more example from chapter 14. This is the final exercise on the chapter 14 handout. It's example 4. It says the accompanying table lists survey results obtained from a random sample of different crime victims. At the 5% significance level, test the claim that the type of crime is independent of whether the criminal is a stranger. So we have the different types of crimes here. So we have homicide, robbery, and assault, and then whether the criminal was a stranger or the criminal was an acquaintance. So here's my contingency table. So we have 2 rows, 3 columns. And like I did in the last example, if it's helpful to kind of add the grid lines, you can do so, but it's not necessary, just a matter of preference. And in this example, I didn't give the row or the column totals. So the first step is to formulate the hypotheses. So we're testing to see if the type of crime is related to whether the criminal is a stranger. So we're going to assume for the null hypothesis that those 2 variables are independent. So type of crime and whether the criminal is a stranger are independent. Then the alternative is going to be that there is a relationship between the two. So that type of crime and whether the criminal is a stranger are dependent. So that's our alternative hypothesis. And we're testing at the 5% significance level. So alpha is 0.05. So let's go to step 2, determine the model to test the null hypothesis and analyze the sample data. So we can calculate the degrees of freedom. So that's always going to be the number of rows minus 1 times the number of columns minus 1. So we have 2 rows here. Criminal was a stranger, criminal was an acquaintance. So that's going to be 2 minus 1 times the number of columns minus 1. And we have 3 columns, 1 for homicide, 1 for robbery, 1 for assault. So that's going to be times 3 minus 1. And this is going to give us 2 degrees of freedom. So we can now calculate the test statistic and we'll label it on the curve and then we'll find the p-value. But first we have to enter our data into a matrix. So enter data into a matrix. So let's go ahead and do that now. And if you'd like, you could even pause and enter this contingency table above into a matrix into your calculator. And I'm going to do the same thing as well. So to get to your matrix screen in the calculator, press second and then matrix. I'm going to edit matrix A again. So this is our matrix from the last example. This one is still 2 rows by 3 columns, so we don't need to change the dimension. So we could hit enter twice, and that's going to bring us now to the entries. So we could type in our new contingency table. Okay, so there's my contingency table. And now we're going to perform a chi-square test. So we could press stat. We arrow over to tests, and it's option C, chi-square test. The observed is the matrix where you just entered the contingency table. I said to always use A because it's just easier because it's already there from every previous time we do one of these, we've been using A, so we don't have to change that. And you could leave the expected as B because that's just where the calculator is going to store all the expected values that it's going to calculate. So we can arrow down to calculate. So we get a chi-square test statistic of 119.33. And we get this p-value of 1.22 e to the negative 26. So remember, there was a question similar to this in the chapter 10 and 11 lectures, hypothesis testing on means and proportions. I don't remember which one it was, but remember we got a p-value that looked similar where the calculator gave us scientific notation. And I explained it to you on the whiteboard, so I'll just give a quick reminder that whenever we have scientific notation, like in this case, it's 1.22 times 10 to the negative 26 power. That's what the calculator's telling us right now. So we have to move the decimal place back 26 places. So we're going to have 0.00000, 25 zeros, and then the 1.22. So this is approximately 0. This is a very, 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 very tiny p-value. So let's write this down. So the test statistic is about 119.33. And remember what I said a couple of lectures back when I introduced chi-square, that the larger the test statistic, the more likely it is that we're going to reject the null hypothesis, because the larger the test statistic, that means that there's a larger difference overall between each observed value and the expected value for each cell in our contingency table, which would be indicating that there's some sort of dependency. So p-value we said is approximately 0. So let's label these on the curve. So chi-square is equal to 119.33. That's my test statistic. The p-value is going to be the shaded area to the right. And it's approximately 0. Very, 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 very tiny p-value. So our decision rule is that we only reject the null hypothesis if our p-value is small enough, which is less than alpha, right? That's the rule. We only reject the null hypothesis if the p-value is less than alpha. My p-value is very tiny. It's approximately 0. And my significance level is 0.05. So 0 is less than 0.05. So since the p-value is less than alpha, we do reject the null hypothesis in favor of the alternative. And the alternative is that the type of crime and whether the criminal is a stranger are related. So we can conclude that type of crime and whether the criminal is a stranger, they are related or dependent. Okay, so type of crime and whether the criminal is a stranger are in fact related. There is a dependency.